Good afternoon, everyone. This is Brenda Choco, and I'm going to discuss to you about the primitive counting in the ancient times. So before we start, let's play this video first.
History of numbers. Most primitive men counted up to 10 or the total number of fingers on their hands. Others counted up to 20 or the number or the numbers of fingers and toes. As men became more civilized, they used sticks, pebbles, and shells to write numbers. They set 3 sticks or pebbles in a row to show that they meant 3. Others made notches in a stick or tied knot in a rope as a means of writing their numbers. When you count on your fingers, it doesn't matter whether you start with your thumb or little finger. But among primitive people, there were set rules. The Zuni Indians started to count with the little fingers of the left hand. The Ottomans of South America began with the thumb. Basically, zero came in origin in 5th century AD. Zero was invented independently by the Babylonian, Mayans, and Indians. Although some researchers say the Indians' number system was influenced by the Babylonian got their number system from the Sumerians, the first people in the world to develop a counting system. In the Western Hemisphere, with no contact with the rest of the world, the Mayas of Central America developed one of the most remarkable of the early number systems. They made their numerals using only 3 symbols, a dot, a straight line, and an oval. Mesopotamia about 3000 BC. Their simple numerals 1, 2, 3 were copies of the caveman's sticks or notches. It is interesting to note that in many of the numeral systems found throughout the world, one was written as a single stroke, like a stick, or as a dot, like pebble. How they add. It is something to know that 3 sheep plus 2 sheep always equals 5 sheep, or that 3 urns and 2 urns are 5 urns. It is a big step to realize that 3 of anything plus 2 more of them make 5 of them, or that 3 plus 2 is equal to 5. Here is the notation system. Each power of 10 had a separate symbol. They did not consider place value. Babylonian numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. Babylonian numbers.
So that's it. That's the short background of the primitive counting in the ancient times. Now, let's define first a number. So number, it is the fundamental abstraction. And there is archaeological evidence of counters and counting systems in some of the earliest of human cultures. In early civilizations, counting and measuring become necessary for administration. For numbers on agriculture, that there is a keeping track of the amount of land allocated to a farmer, the quantity of the harvest, and any taxes or duty to be paid required a well-developed system of measuring and counting. Numbers and abstractions, it is something to know that 3 sheep plus 2 sheep equals 5 sheep, or that 3 urns and 2 urns are 5 urns. It is a big step to realize that 3 of anything plus 2, more of them makes 5 of them, or that 3 plus 2 equals 5. The pure numbers are abstractions. Only a civilization that has a well-developed written number system and has discovered rules for manipulating those numbers has the chance of moving on to science. Then a look at a number system and rules of arithmetic of 2 of the great ancient civilizations. These are the Egypt and the Babylonia. The Egypt is one of the world's oldest civilization. The ancient period was from about 3000 to 300 BCE. During this during which this civilization had agriculture, writing, and a number system. The settled area of Egypt is a narrow strip of land along the shores of the Nile River. Egypt would not be possible without the waters of the Nile. Because of Egypt's isolation from possible invaders, it was able to develop into a stable, prosperous country through agriculture. The Nile River flooded every year in July. The floods provided rich nutrients and silt that made very productive soil. Egypt subsisted on organized and centralized farming in the area flooded annually by the Nile. Tracking and managing the allocation of land required extensive record keeping and written language. Hieroglyphics, this was the uh, writing system on the Egypt. So this is the picture as have shown. Hieratic, for everyday use, a script form of hieroglyphics evolved called hieratic. This is from a letter written by 1790 BCE. The Egyptians' numbers, a system of writing numbers emerged from hieroglyphics. A number was written as a picture of its components. The base of the system was 10 like ours, but the notation was completely different. So here is the notation system of the Egyptian numeral hieroglyphics. Each power of 10 had a separate symbol. The order in which the symbols of a number was written was not important, or there is no place value. So these are some examples of written numbers: 276 and 4622. For fractions, as I've shown, 1/3 and 1/5, all fractions represented a single part of a larger whole. Sample 1/3 and 1/2 as above. The symbol for a fraction was to place an open mouth above the denominator. These are the hieratic numbers. The number system was cumbersome, so a shorthand version was developed for use in hieratic. But the hieratic version had even more symbols and still no place value. 1, 2, 3, and so on, 10, 20, 30, multiple of 100, all were separate symbols. Despite the cumbersome notation system, the Egyptians developed an extraordinary efficient method of doing arithmetical calculations. Okay, by the way, the multiplication and division by doubling. Calculations were done by a series of steps requiring doubling numbers and then adding up some of the results. Okay, here are the knowledge required: how to add and how to multiply by 2. Not required: how to multiply by 3 or 4 or 5 or any other number. Example number 1. 13 multiplied by 24. In 2 columns, write the number 1 in the left column and one of the above numbers in the right column. Generally, choosing the larger number to write down works best. In this example, the 13 will be called the other number. As a continuation, double each of the numbers in the first line and write the result in the next line. Do the same to the numbers in the new line. Continue until the number is in the bottom left position is more than 1/2 the other number. In this case, that is 13. Now, place a tick mark by numbers in the left column that add up to the other number. The best procedure is to start from the bottom. Here, 8, 4, and 1 are chosen because 8 plus 4 plus 1 equals 13. Then, For every line with a tick mark, copy the number in the second column out to the right. Add up the numbers in the right-hand column. This works because 1 times 24 plus 4 times 24 plus 8 times 24 equals 1 plus 4 plus 8 times 24. That is 13 times 24. For example, number 2, 246 times 7,635. Okay, here is the solution. Next is the division via doubling. Use the same process for division, but go about it somewhat differently. This time, you double the divisor successively, stopping just before the number which would be greater than the dividend. So here is the terminology for 100 divided by 25, that is 4. 100 is the dividend, 25 is the divisor, and 4 is the quotient. Example, 300 divided by 14. In two columns, write the number 1 in the left column and the divisor in the right. Now, double the numbers in both columns until the last entry on the right is more than half of the dividend. Here, the last entry is 224, since doubling it gives more than 300. Place a tick mark beside the entries in the right column that add up as close as possible the dividend without exceeding it. Then copy the numbers in the left column on the same line as the ticks into a separate column and add them up. This gives a quotient 21. As a check, add up the tick number in the right column. This gives 294. So, 14 goes into 300 a full 21 times with a remainder of 6. The division process does not give exact answers, but it is good enough. An arithmetic system for practical use. The main problems that a scribe would have to solve were such things as determining the area of a plot of land assigned to a farmer, a multiplication problem, or dividing up some commodity into equal portions, that is a division problem. Now let's go on to the Babylonia. Babylonia is the civilization that developed in Mesopotamia around 1800 BCE, succeeding the Sumerian civilization, which had collapsed by then. The Babylonians used the cuneiform system of writing on clay tablets with reed styluses. The Babylonians had a complex and prosperous culture and pursued many interests. Because of the durability of cuneiform tablets, much is known about their civilization. Throughout the Mesopotamian civilizations, from Sumer to Babylonia, a unique number system was used based on the number 60, not on the familiar base 10 used in most other cultures. Here is the sexagesimal numbers. In the sexagesimal sample 60-based system, there are different combinations of characters for each number from 1 to 59. Then the symbol for 1 is used again, but this time meaning 60. The symbol for 2 always means 120. The symbol for 3 also means 180, and etc. Place value system. Compared to the Egyptians, who had totally separate symbols for 2 and 20 and 200 and 2000, etc., the Mesopotamian or Babylonian system used the same symbols over for the next higher level. Note that we do the same, but we place zeros behind them to indicate the level. Using the marsh reeds as a stylus, Mesopotamian writing was done on wet clay tablets by pushing the end of a reed stalk into the clay. Here is the vertical character for 1. If the reed is turned with a thick end up and pointed end down, it is the symbol for 1. Here are the numbers from 1 to 9. The horizontal, on the other hand, the character for 10. If the reed is turned with a thick end to the right and pointed end to the left, it is the symbol for 10. Counting by tens. Okay. 10, 20, 30, 40, 50. So those are some examples. The numbers from 1 to 59. What comes after 59? 60 in the sexagesimal number system is the basic unit at the next place value. So, it looks just like 1. That is 60. Or 1 times 60 or is equal to 60. Example, that one. In 9 times multiplication table. Why choose a base of 60? Most cultures have number systems based on 10 or perhaps 5 related to the digits on our hands. But 10 is a poor choice for dividing evenly into parts. It is only divisible by 1, 2, and 5. The number 60 can be evenly divided by many smaller numbers, which are 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. So the fractional parts are much easier to express exactly. Any unit can be divided into parts of a lower place value by dividing it by 60. Just as 1 minute is equivalent to 60 seconds. 1/2 of a minute is equivalent of 30 seconds. Seconds is the next lower division of time after minutes. The sexagesimal system today, we still use the 60-base counting system in 2 places, keeping time in hours, minutes, and seconds. Also in measuring angles in degrees, minutes, and seconds. Why? Timekeeping and detailed astronomical observation came from the Babylonians. Greek science made use of Babylonian data and kept their number system for that purpose. In our decimal-based system, we use the same numerals over and over again to mean numbers of different sizes. But we can tell which size is intended by the use of zeros and decimal places. Example, 27,900 is bigger than 279, or 98 and 6/10 is smaller than 986. In the Mesopotamian or Babylonian system, numbers that are 60 times larger or 60 times smaller are all written the same way. Because the orders of magnitude are separated by factors of 60, there was rarely confusion in the early centuries, but ultimately this was a severe drawback in the system, as society became more complex. So that's all for my discussion about primitive counting. Again, this is Brenda Choco. Thank you.